Michele MAGNO, Head of Project-Based Learning Center of Zurich. Michele is a senior scientist and head of the Project-Based Learning Center at ETH Zurich. He's working in ETH since 2013 and has become a visiting lecturer or professor in several universities, namely the University of Nice Sofia, France, ENSAT Lannion, France, University of Bologna, and Mid-University of Sweden. Dr. Magno is a senior member of IEEE, the finalist of ETH Spark Award 2018, and the recipient of many other awards and grants. His background is in computer sciences and electrical engineering. So help me in welcoming Michele.
Okay. Okay, so thank you very much, Thomas, for the very nice introduction. And of course, as you see, many names here, because in reality this work is done in cooperation with a group of Professor Benini and many PhD from my group and this group, and you will see why. So first of all, as you see for the title, in this presentation I'm ranging from the high tracking and the small-scale drones, and what they have in common. So maybe you can think about it, and it's very hard to see the similarity, but in reality, what I'm seeing in this presentation is that both they need to be extremely efficient, especially because when they are battery operated, and often, to say always, they need low latency. For eye tracking, we need the latency in the range of below 10 milliseconds to eventually give a feedback to the user or to have a human-machine interface. For the drones, especially if you want to activate object avoidance or any other task from the drone, you need also a similar latency. And especially you need to process this information in local. Because with this millisecond, you cannot even think to transmit the information in any existing wireless communication because the latency will be over these 100 milliseconds that you need. So it's the perfect application scenario, in my opinion, for tiny machine learning community. And more we are stressing in small devices, battery-operated devices, drones that are small, and we'll show also why this drone can be not only toys, but also a reality. More we are going to use all what we are learning in this tiny machine learning community. This is the reason why, in general, I'm trying to bring in this presentation a different activity we are doing. In this case, I selected both, even if the same is different. And the other reason why we are making them in common, even if you, for my today presentation, will see more the drone rather than the eye tracking, is because in this particular let's say, sub-area of my research and our research, we are trying to exploit two emerging technology, not only for tiny machine learning, but also in general, that are actually pushing on going toward energy efficient and low latency. So back to the original application scenario of eye tracking and drone, even if they can use for many other things. Fortunately, people before me, so I was very happy to see the agenda, because actually before me were prophecy talking about the device camera, other people are talking about device camera and neuromorphic, so you should be quite an expert now to see what are the potentiality. And what I want to show today is actually, I'm more an embedded system person, even if my background is in electronics, so I'm really between hardware and software. And basically, we will see how we can use commercial device camera for improving the energy efficiency, exploiting an academic processor that is a real chip, so it's not academic processor that stay in the simulator, that is a real chip that include many different subsystems I'm going to talk in 1 second. But is an academic processor that includes everything you need for getting information from the device camera without need of any other interface, process the information. You can decide if you want to use this processing capability for an accelerator that is a spiking neural accelerator, or use a traditional deep neural network, and you can even control your drone that you will see even a little demo later. I hope it's still working, but we will see. So in general, these are the two potentiality. And another use case I want to show, also to stress, because we are in a tiny machine learning community where I'm expecting to see processor power that is in the range of milliwatt of power. Not megawatt, not watt, even not hundred of milliwatts. In general, for tiny machine learning, we are pushing on going in the range of 50, 100 milliwatt for all the system. This is what we are going to see later. So for this power, what you will see, what you can even imagine that I'm showing today, it's already done for many commercial drones. So if you ask me why this is not done, so these are already saw it, yes, this is true, but these very commercial drones, they have much more computational power and also much powerful propeller. But in general, we are talking to two different, completely different systems. Even this, that is not the bigger drone you can see, is anyway some things that has a battery of 5,000 mAh, and in general, this can host a Jetson, Nano, or Jetson, or in general, a GPU without any problem. So for a few minutes, but it can do. And more you go in this area, more, let's say, the algorithms are consolidated, you have less power, less problems, but of course you have problems. But what I want to focus is that we are going to see how we can bring algorithms, a new technology, really energy efficient, and in a small nano drone, especially for the limit that you have in space that automatically limit the battery. So actually, if you came here a few minutes ago, you were seeing that I'm going to change the battery. This battery is a few centimeters. And already the propeller are consuming, so few millimeter means that, few centimeter means that we have more or less 250 milliampere-hour. The propeller already consuming 1 watt. The space for the computational resource of the sensor is back to this 50 milliwatt that I was mentioning before. So we need to be even more efficient in sensors, and this is also the reason why I like a lot the voice camera, and in the processing to really get what maybe you saw already in other demonstration in a small little drone. And you need to be also more creative, you need to make sensor fusion eventually, but in this case I'm going to propose some things with event-based camera and this novel processor. And in particular I also want to stress in some things interesting. So if you see any demo with the voice camera from previous work, and I'm, my friend is from Prophecy, so I can say also some things. Prophecy also is a wonderful camera, but today you need to supply with USB or with some other device to work if you buy the commercial one. And the most of the works, not the Prophecy work, most of the work that are using the voice camera for drones are today still using a event fetch by USB, and especially they are using often the information, if they are doing the full flow from sensor to control, the information are processed by a Jetson, back to the power we mentioned before. And especially it's very hard to see some real neuromorphic processor embedded in a real field and a real drone. So in general, there is few that are using academic processing like lowly, that is not really meant to control a drone. You need to connect anyway to a Jetson to then control a drone or to another microcontroller. And it's very hard to see an end-to-end evaluation in how much speed, so a real end-to-end from the sensor event to the control of the drone, how much is the latency you're getting. You see many other devices you can, of course, work with. We are doing the same. So we are also taking data set to make evaluation. I'm not saying that we are there at the moment, but the idea and the contribution of this work that actually we published recently in a conference that was held 2 weeks ago was really having a full platform where we can exploit this novel processor to really get information from the voice camera, make your algorithm, and really test your end-to-end millisecond. And I can show you some interesting data on the milliwatt. So I'm not going to see, the demo you will see is actually not with some things still working because we are still working on it, but more to present this platform that uses this processor and can be used for a real end-to-end evaluation in ultra-low power way, where low power is in the range of milliwatt. Let's go back to what is this chip. This, as I mentioned, was designed and manufactured. So there is the tape out. We have a real chip. You will see later this chip that is a quite interesting new microcontroller because it's including the system on chip domain. Is a chip. It's like a real microcontroller. You can connect a serial port. You can connect even your PWM motors controller here. Then we have the cluster domain that is the one that can support is supporting 8 RISC-V cores, very similar to the PULP platform or the GAP8 platform that you can find commercial, and these are the two big interesting parts. So there is a ternary convolution accelerator where you can run all your DNN accelerator. So you can really use it like a normal hardware accelerator, and there is the opportunity to even use directly spiking accelerator. On top of it, I think what is also quite interesting, and this, remember, is if you see the chip now means that the work was started 2-3 years ago, was that even now is difficult, but at that time it was even very difficult to find an interface where you can directly get spiking event from any camera. And the good things of this work is that we really included two different interfaces. You can connect directly. Of course, the difficulty was that the device camera, it's a promising and moving sensor, so it means that there is even not a common camera for all the vendors' cameras. So we select a single one. So unfortunately, this interface is quite proprietary. So it's an Inivation camera that you have here, and there's only one model of this Inivation camera, because of course this takes 2-3 years to arrive to this level. But I want to show more the potentiality of having interface inside the microcontroller rather than having a generic purpose microcontroller. But you will see that this already can work and do some things interesting. Then we also attached a CPI, okay, we can also see from here, a CPI interface for attaching a low power IMAX camera to have also RGB. Why? For many reasons. You can have a robustness making sensor fusion between RGB and device camera. I also remember that we inserted two different hardware accelerators. And again, this for us is still a test platform to really evaluate the end-to-end information, our model, our sensor fusion is really some things that we want to stress on using it. And at the end, we really use this, we designed this evaluation, still an evaluation board, but can fly in a bit bigger than this drone platform that are commercial frame that you can buy, and the flight controller, in this case, is a commercial flight controller that can directly accept the PWM signal that are coming from internal the microcontroller. So it's really a full system. You can really build your own neuromorphic or mixed neuromorphic RGB, or in general only RGB, but in general you can build your fast, energy efficient drones using this novel camera. And why I'm saying this is quite promising, again, we have the limit of a camera, yes, this is true, if this is a limit for somebody, but many people can use it, but in general, this camera is a camera that has only 132 by 104 pixel. Of course, there is no magic in electronics. This is also due for the limited of my memory. We can go a bit higher, but we will not reach probably 2 megapixel. But in general, for our needs was enough. And this is the only camera that can be interfaced to this platform, and the frame camera can be generic because there is a generic CPI interface. So these are a bit the information. So I want to arrive to the demo. So in general, these are, let's say, more specification, but we really reach the goal to have a full working microcontroller. And actually, we found out some things very interesting. So we found out that thanks to our interface, first of all, this was already a lot of work, so I'm very happy to see that we can really make it work. So we can really take the two images from a normal RGB and especially the voice camera. These are directly in the memory of your microcontroller, so you can process all of your neural network or spiking neural network. Also, you can also process it like a normal DNN to see the object. But one thing is interesting is that we were really, really able to get the minimal power from the camera chip. So the chip that Inivation gives us is only the single sensors without any interface, because we are interfacing internally. And this we were able to get half milliwatt of power. And I'm pretty sure that any commercial camera to buy, but not because they are not good to it, but they have another goal, providing data to a PC with USB. But if you attach any USB camera, you will get something in the range of watts. So this is the only drone that can really go below few milliwatts of power thanks to this interface and, of course, with the limit of this camera. But also we see some other interesting things that we saw that actually what we were seeing with the USB interface attached to the same camera done by Inivation, the company that provided it, actually we could even overperform it. Because if we use the same interface directly in the microcontroller is able to get 7 times more throughput of the data. Means that in reality you can go 7 times faster than what you can get with a USB camera. You need or you don't need, this is secondary at the moment. Plus all the flow, including the camera and our front end. Of course, front end is consuming power because you need to process and to take this information to transfer in memory, is anyway consuming inside the chip only 10 milliwatt of power. So this is some things that start to be, at least for us, quite interesting, because we're really pushing on going in our goal to stay below the 50, 100 milliwatt of power to have a full neuromorphic fast micro drone or nano drone. So this, and we have even a surprise. We can go even 7 times faster than we were expecting. This we cross-check with Inivation. Actually, this we really reach the limit of this camera can do. And then if you do a bit of comparison, what is existing, maybe there is some new work that is not compared here, you can see the difference. And again, not because we are better, it's because we take the problem for attaching the sensor to redesign a microcontroller with low power in mind. This microcontroller is quite unique because it can have this hardware acceleration in milliwatt of power, and this brings the gap of 1 watt or more of the existing system using device camera for drone to 35 measured power. So this is the power that if you take the other platform that you have in Zurich that we show later, you measure exactly the power that you're getting, you don't get for the hardware platform, not for the propeller, 35 milliwatt of power. And in total, you can have with the sampling and the inference in the range of 46 milliwatt of power. So it means that you have 10 for the the front end and 35 to run your spiking neural network on it. And this, then we started to work also in terms of efficiency. How good is our network to, or how good is our spiking neural accelerator to process some neural network. In this case, I think we are still in a preliminary work. This means that, for example, we didn't implement a full object avoidance. This is also the reason why I don't have the demo here, also because I think the new drone is still under, we are debugging it, and it won't kill anybody here for flying somewhere else. But in general, we started to see a generic network. This was a network we implemented for a gesture recognition, but in this case, it was more the goal evaluation rather than the use case. And we see how much we could do. So here you can see the network is a medium-sized network, and we are getting under 63 milliseconds measured power. So we believe that this can go down, but this is the moment that we are measuring. And as I mentioned, you can find all the details that you find in this presentation in this paper that we publish, including the network, and we are planning to release all this network already, so you can do the same measurement that we get. But in general, we were very happy because we found out that anyway we reach a few milliseconds. The interface takes only 32 milliseconds after processing the data. The spiking cluster is a bit slower, but I feel we have some bug to solve there. But in general, we were very happy to see that an end-to-end energy consumption was only of few millijoule, and especially we were in the range of 150 or 160 milliseconds, and this is quite promising for the future. And I close a bit this chapter because I want, first of all, arrive to the demo. I think I have a few minutes, and especially I want to see the connection of eye tracking. For eye tracking is another project, so actually we are designing the board that has the same Kraken chip. So inside here there is the Kraken chip and the same DVS camera. The reason is not because we want 100% this camera, because maybe other camera for Kraken could be better, but the interface for see this number is only linked to this camera, and we designed this like, again, a evaluation board to get eye tracking. This project is actually a bigger project because it's funded by InnoSwiss, that is an industry and research community or grant foundation for us, so that is funding this project. In this case, we are working to convert the YOLO in a YOLO spiking running in SNN. We are seeing that the preliminary result that we are estimating will be in the range of 1 millisecond. So this probably we are going to publish in November, so I think this thing is, some things is going, we have already the data set, but I think the benefit of energy and latency can bring also to NI glasses. So why we need this 50 milliwatt of power, why we need to be very fast? Because in the glasses you will not have, if you don't have some things attached to your PC for gaming, this is okay, but if you want to really have tracking when you are driving your car without attaching your glass in the car, you need to stay in this milliwatt that you saw. Even actually you need to do this right to go down. So I think these are interesting, promising technologies, not ready, of course, so you have 2 years to do it, but I think it's some things that we are going to see it. So what I want to conclude and then arrive to the demo, this demo is based on other sensors that I will show in 1 second, but in general we were very happy to have the first real embedded system in the form of a drone that can really run end-to-end evaluation on the processing. You can test your algorithm with a real spiking event coming from a camera and really reach the minimal energy and latency that you can have, and we can see some preliminary, so actually this is not preliminary, this power is the measured power that you can reach for the full system working, so from the camera to the microcontroller. And I think this is quite promising actually. If you want continue or work in any cooperation, I think this will be happy to work on it. And to go back to the toys that you are seeing here, so this, when I show this to my 3 daughters, they always think this is a toy for them. But in reality, these are not really toys. So in reality, this can be used for many other application scenarios where you go in very small spaces, where you go in a location, indoor are perfect. Of course, if you fly it outdoor, probably this is crashing very fast because the wind is bringing it away if you are not in perfect condition. But in general, these small drones are not only let's say, a playground for us to really stress in energy efficiency, but there are some things that can solve some application. In this case, to safety for you, for me also, and for everybody, we switch in some other topic that we are working. So in general, we are working by mistake I cancel, so I will explain it. So there are, instead of the DVS camera, so we are not using DVS camera here, we are not using Kraken. We are using STM32 microcontroller on top of the Crazy Flight, that is a commercial board, where we attach our deck, and we have 4 different time-of-flight sensor 8x8 that are produced by ST Microelectronics that really give you the depth map. So basically, I want to show that the drones can be really fully autonomous. Actually, no, the other people show that these I brought here only 2 minutes ago. I tried only once. I even changed the battery, so I don't know what will happen now, but we try anyway. So he never saw this environmental, and he will be able to land, to take off alone. He will be able to avoid me and avoid you, and try to go back here or in this area for the landing. Of course, not only he can do the job, because actually he has only 40 seconds to do this job. So I hope it's working. So if it doesn't work, I put I have anyway the backup video, but let's see if I can reach the goal. 1 second, I will do again because I removed the battery in the, okay, maybe it's not working, but I will try again because I took away the wire from the battery, so I don't know what will happen now. Okay, so basically it's landing alone, so now you see, okay, that is doing nothing. In reality, it's avoiding everyone. So avoiding me, avoiding you. Now you see even the hole, so this is the worst condition that I could put him, because he needs to come back here. So he's trying to come back here, but he needs to avoid me, so it's like a catching system, and he has 40 seconds to do it. Meantime, you can see there is no condition that so I have nothing to remote control it. And in general, now he's trying to see where are the landing, and I can make easier the job, because now he's in quite okay position, so I don't go. Okay, maybe he's anyway flying away, but after 40 seconds, he will decide to land wherever is safe for him, and this is the demonstration that it's working, and I think means that there is, again, a lot of people working on it, and there is a mix between sensor fusion, there are different sensors, and the tiny machine learning that is working here. I put also the safe video, because this is actually how we are training, so you can see that actually I even speed it less, because again, I don't know where the people, I didn't know anything about this room before. I just arrived yesterday, this morning is the first time I put it, And you can see that this is can even really faster close it. Again, this is not the device camera, but this is really more to show that tiny machine learning can be very useful for putting autonomous on it. And this, as I mentioned, is an STM32. I'm showing the STM32. We have also many versions with GAP9, GAP8 that are more memory, more computation resources to show that it's possible even in very, very small network doing it. Of course, more you have capability, more you can do some things more complex, like landing back. Or my dream, asked to my PhD, but they say no, was that really throwing it somewhere and coming back in my hand. But I think this we will see maybe in 1 year with another processor. So on this, I want to conclude. As you can see, actually, we have really it ready for a couple of them only for potential cooperation, and we are investigating many different areas. So we are not linked to the drone, but it's wherever there is energy efficient and latency, I believe this kind of platform can be quite useful. So I think if there is any cooperation, I will be happy to support. I wrote some names at the beginning, but I'm pretty sure I forget some other. But this work, many of these work were done by many persons, and especially the group especially the project with Kraken was done with the group of Professor Benini. That's it. I'm open for question. And thank you.